Hi, my name is Boris from BioSense Institute, and today I'll be presenting you a joint work with my BioSense colleagues, Nina Pajevic, Vladan Filipovic, Dimitrije Stefanovic, Nemanja Djuric, Marko and Zeljana Grbovic. Our research is on exploration of data augmentation techniques for bush detection in blueberry orchards. A little bit of our motivation for this research, as the object detection has a potential that is largely untapped in agriculture. The precision tasks like orchard navigation are crucial, yet underdeveloped, as from our knowledge, most of the object detection is done for tree trunk detection, as it can be seen on the images on the right. And we propose that data augmentation can significantly enhance detection performance in object detection in agriculture, and especially in the blueberry orchards problem. A little bit of our data set before tackling the data augmentation part of it. It's an expansion from a data set from previous year, where last year our data set had 2,500 images, and now it's expanded significantly to 7,250 images. All the data has been captured in Babi, Serbia. It's in central Serbia, on a robot platform called Gary, and using the OD cameras with a RGB images format. Now, here how some of the scenes in our dataset look. We can see the basis of blueberry bushes, and we can also see poles, where the poles can be poles that support netting for the hail protection of the orchard, or they can be lampposts or poles of any kind that can damage the equipment when taking soil samples or something similar. So it's important to detect them. We can see that in our case, we have occlusions, some shadows, irregular scenes, some backgrounds. So it's a difficult scene that is something usual in agriculture. We also need to know that our data set does have some limitations, that all the data has been captured during the same season, during daylight, so we don't have night or some rain, snow, and some variations that can also happen in these scenes. This is where data augmentation comes into place, where its role in our research is to mimic and simulate these diverse environmental conditions that can happen. We've implemented various segmentation techniques to mimic these real-life variations. Some of them can be seen here. We'll start and just quickly go through each one of them. We have color augmentations, where we've tried mimicking the different times of day and different seasons while altering the HSV values of an image. We've altered positions, perspective, rotated, flipped images, and geometric manipulations of an image to simulate the way as a UGV is going to go over uneven terrain in a blueberry orchard. We've also combined multiple images into a composite scene to expose the model to diverse scenarios that can happen in an orchard. We added noise to the images to simulate some sensor imperfections, some damages to the cameras getting dirty. We've erased parts of the images to simulate the occlusions that can happen. So maybe if somebody left some farming equipment, or if another object is located in front of a bush, our model needs to be prepared for that as well. We've integrated bush cutouts and different background scenes, trying to create completely new scenes on their own. We've also did some mix-up augmentation, where we've overlaid bushes in one in front of each other, so the model can get used to bushes being in this position, as it's also normal in an orchard. A thing that we've also researched in our paper is generative augmentation. It's a thing that holds a lot of potential in the future, from our belief, as it can generate completely new scenes, new images that the model hasn't seen before. We can see on the left some of the original bushes and the ones on the right that we've generated. Now, it is important to note that these generated images, if they're not of the highest quality, as we see later on, can do quite contrary and not improve the performance of the model, but weaken it. And well, when discussing that, let's first discuss on how we did the experiments. We did them by generating a 30% new data and combining them with the original data set. And this new data was generated as applying each of the augmentations we mentioned to it, and then combining with the original data. We've used the YOLO-V8 nano model for running the experiments, as we have good experience with the YOLO models in real-time object detection from our previous work. Now, here's a quick overview of our results. We can see above the dashed line the single augmentations, and below are some combinations we'll discuss in the following slides. As for the single augmentations, we can see good performance with the geometric, mosaic, mix-up, and collage augmentations. They've been bolded with the metrics have been bolded, so we can see which metric has each of the single augmentations improved. Also, some of our candidates that we had high beliefs in as color didn't really improve the model that much. We hypothesize it is as the test and validation data is also captured during the same season and the time of the day. So implementing some variations in the lighting didn't affect the performance that much. Now, we've noted the best augmentations here, as I mentioned, and then we've combined them into the combinations, believing they can bring each of their benefits to the mix, and we'll get a combination that's going to improve all of the metrics compared to the baseline, and something like that did happen, as we can see with the full combo augmentation. Now, about the approaches in the combinations, we've tested out the three approaches: a uniform combo and a full combo, where uniform implies that we've applied one of the four augmentations to a quarter of the additional 30% of the data we generated. The combo means that we've applied each of the four augmentations to the 30% of the data, and the full combo means that we've expanded the original data set by 30% using collage, and then the remaining three augmentations, geometric, mix-up, and mosaic, have been applied to each of the 130% of the images, and that is the way that acquired us the best results. So here is also a qualitative comparison. On the left, we can see the baseline of the model, and on the right, we can see what our combination has brought to the table. We can see quite a improvement as all of the bushes have been detected, where on the baseline that was not the case. We can also see that the bushes that have been detected are the smaller bushes, where our baseline model had problem with identifying those kinds of objects that are far away. So as a conclusion, we can say that we've developed a systematic framework to test individual augmentation techniques, and then later on, using our combination approach, combine them into having a tailored augmentation for your data set. We'd like you to try out this way of augmenting your data in agriculture and see if it can carry on from the blueberry bush orchards to some other use. We plan in the future to intensify our research on generative models, as we believe that they can improve our augmentation toolkit quite significantly. Thank you for your attention.